Hello my dear children, once again welcome to your physics class. So we can continue with the revision of the rest of the topics. In the previous sessions we had discussed all the chapters till thermodynamics. Today we are going to discuss thermodynamics chapter, oscillations and waves. So in thermodynamics we are discussing only the major concepts. So first concept that I want to discuss today is zeroth law of thermodynamics. So what do you mean by zeroth law? How will you state zeroth law? Zeroth law states that two systems in thermal equilibrium with a third system will be in thermal equilibrium with each other. That is, suppose you have two systems A and B, and suppose these two systems are separately in thermal equilibrium with a third system C. Then temperature of A will be equal to temperature of C. Also B is in thermal equilibrium with C. So the temperature of B and C will be equal. So if this condition is satisfied, then we can say temperature of A will be equal to temperature of B. Okay, so this is zeroth law. And zeroth law gives the concept of temperature. Okay. Now next law is first law of thermodynamics. First law of thermodynamics states that the heat energy supplied to a system is partly used to change the internal energy, and rest of the energy is utilized to do the work. Okay, so this is the mathematical expression for first law of thermodynamics. And next is some important thermodynamic processes. So first is the quasi-static process. And what do you mean by quasi-static? Quasi-static process is the process which takes place very slowly, so that at each point of the process we feel that the system is in equilibrium with the surroundings. And the next process that we discussed is isothermal process. So in isothermal process temperature remains constant. And next is adiabatic process. In adiabatic process there won't be any exchange of heat between the system and surroundings. And the work done in isothermal process expression is W equal to mu RT ln V2 by V1. So here this you can expect a numerical from this part. So for that you know R is the universal gas constant. So you must study the value of capital R, and also you must know to calculate the logarithm values of V2 and V1. So values will be given for V2 and V1, and you must know to calculate the logarithmic value of V2 by V1. So for that you buy a Clark's table. It will be useful for you your board exams as well. So by a Clark's table, there you can easily find out the logarithmic log values of any number. Okay, and T is the constant temperature, and you should always express the temperature in Kelvin. And you know 1 degree Celsius is 273 Kelvin. Now, in adiabatic process, how will you calculate the work done? So, work done in an adiabatic process is 1 by gamma minus 1 into mu R into T1 minus T2. So, T1 and T2 will be given, and mu R is the universal gas constant. Gamma is the ratio of specific heat capacities, that is Cp by Cv. Okay. And here isothermal process can be isothermal expansion or isothermal compression. So if isothermal expansion, final volume V2 will be greater than the initial volume V1. So if final volume is greater than initial volume, work done will be positive. Okay, so for an expansion process, work done will be positive. But at the same time, for a compression process, the final volume will be less than the initial volume. Work done will be negative. Similarly, for adiabatic expansion process, work done will be positive. And for adiabatic compression process, work done will be negative. And next is the second law. So two statements are there for second law. One is the Kelvin-Planck statement and another is the closure statement. Okay, so Kelvin-Planck statement states that no process is possible whose sole result is the absorption of heat and conversion of that heat into work. That means it is not possible to convert the whole heat absorbed to useful work. Some amount of heat energy absorbed is being wasted or dissipated. through some form. Okay. Now closure statement. Closure statement states that it is not no process is possible whose sole result is the transfer of heat from colder object to hotter object. That means naturally heat will flow from a hotter body to colder body, and if heat is to flow from a cold object to the hot object, that means if reverse process is to be possible, then some external work has to be done on the system. Okay, so that's all about the thermodynamics chapter. And next let's discuss about the oscillations chapter. And you know what type of motion is oscillatory motion. Oscillatory motion is a motion is a to and fro motion. Okay, the object will execute to and fro motion about a mean position. And periodic motions are those motions which repeats itself at fixed intervals of time. For example, rotation of planets around the sun, movement of earth around the sun. Okay, and movement of the hands of the watch in a clock or a clock. Okay, all are examples for periodic motion. And here we can say all periodic motions are all oscillatory motions are periodic. All oscillatory motions are periodic. You consider any oscillatory motion, example oscillation of a pendulum, oscillation of a swing, anything. All oscillatory motions are periodic because all the motions repeats itself at regular intervals of time. But at the same time, all periodic motions are not oscillatory. All periodic motions are not oscillatory. If you consider the motion of planets around the sun, it is a circular motion. It is a periodic motion, but that periodic motion is not oscillatory motion. Okay, so all oscillatory motions are periodic, but all periodic motions are not oscillatory. And in this, the simplest form of oscillatory motion is simple harmonic motion. Okay, simple harmonic motion SHM is the simplest type of oscillatory motion. And a simple harmonic motion can be represented by this expression x of t equal to a cos omega t plus phi, where a is the amplitude of that wave and omega t plus phi is the phase, phi is the phase constant. So this is the way to represent the displacement of a simple harmonic motion, and this graph represents the wave of a simple harmonic motion. Now what is the relation between simple harmonic motion and uniform circular motion? See, is there any relationship between simple harmonic motion and uniform circular motion? Yes, there is a relation and there is a derivation related to this. So you must study the derivation. Actually, the projection of uniform circular motion executes simple harmonic motion. Okay, so this relation is a derivation. I have given that. Refer your notebook and study this derivation. Now, next is velocity of simple harmonic motion. So this is the expression for the velocity of a simple harmonic motion. Velocity equal to omega into square root of a square minus y square. And this velocity is maximum at mean position. That means in this expression it is clear when y equal to 0, velocity is equal to omega into a. So this is the maximum value of velocity, and y is equal to 0 is our mean position. So we can say velocity is maximum at the mean position. And next is acceleration. Acceleration expression is minus omega square y. And when y is equal to 0, here acceleration is 0. At the same time, when y is equal to a, acceleration will be minus omega square a. So acceleration is maximum at y equal to a position, which is the extreme position. So velocity is maximum at mean position, acceleration is maximum at extreme position. Okay, so that's about the velocity and acceleration of simple harmonic motion. Again, refer your note and study the derivation of velocity and acceleration of simple harmonic motion. And next is energy in simple harmonic motion. So the total energy in simple harmonic motion is the sum of kinetic energy and potential energy. And this is the expression for total energy. E is equal to half m omega square a square. And if we look at the values of kinetic energy and potential energy, it is also the same. Kinetic energy is half m omega square a square. Potential energy is also half m omega square a square. So we can write kinetic energy is equal to total energy is equal to potential energy. Total energy remains constant. Then we came across several systems executing simple harmonic motion. First system was that of a spring and another was that of a simple pendulum. So the time period of oscillation of a spring, this is the expression for the time period of oscillation of the spring. Time period T is equal to 2 pi square root of m by k, where k is the force constant, m is the mass of the spring. So this is a derivation. Study that derivation. You can expect that for your exams. And period of oscillation of a simple pendulum, this is the expression. Period T is equal to 2 pi root of L by G. This is also an important derivation. So refer your notebook and study both the derivations very well. Here L is the length of the pendulum and G is the acceleration due to gravity. Now damped simple harmonic motion. What is the equation for damped simple harmonic motion? It is very important and it is not similar to the general equation for the simple harmonic motion. Damping constant will be present in the damped simple harmonic motion, and also expression for frequency of simple harmonic damped one is also important. And in a damped simple harmonic motion, the amplitude will not remain the same. After some time the amplitude decreases with respect to time and finally it becomes zero. And all the oscillations that we see around us in our real world are best examples for damped simple harmonic motion. And due to the resistive forces present in the medium, the amplitude of the oscillation decreases and finally the oscillation stops. Okay. Next we discussed about the free oscillation, forced oscillation and resonance. Okay, so all the three oscillations and the resonance are very, very important. So please go through the forced oscillations, free oscillations and resonance. Free oscillation, if the system oscillate with its natural frequency, it is free oscillation. And what is forced oscillation? If the system executes some oscillation with the help of an external periodic force applied, then it is known as forced oscillation. Okay, resonance condition is achieved if the frequency of the applied force matches with the natural frequency of the oscillating object. So maximum amplitude is obtained at the resonance position. Now you can just discuss one problem, numerical of this chapter. See, magnitude of maximum acceleration in a simple harmonic motion is pi times, this is acceleration, is pi times that of maximum velocity of simple harmonic oscillator. Then what is the time period of the oscillator? So it is given the maximum acceleration of the simple harmonic oscillator is pi times the maximum velocity. So what is the expression for maximum acceleration of a simple harmonic motion? It is omega square a, and similarly maximum velocity is omega a. So if a max is pi times v max, then substitute a max is omega square a, and this is not p, this is pi, and v max is omega a. From this omega and one omega will cancel, a will cancel, we are left with omega equal to pi. Therefore time period t is equal to 2 pi by omega, that is 2 pi by pi, 2 seconds. So similar questions can be expected for your exams. And next we can discuss the important concepts of the last chapter, that is waves. And in waves we came across the standing waves, that is the most important topic. In standing waves, when do the standing waves is formed? See, when the incident wave and the reflected wave combine, we can see a standing wave. See, here a wave is produced in the string and this wave go and hit this rigid boundary. As soon as a wave hits the rigid boundary, it is reflected back with the opposite phase. So this is the reflected wave. Okay, so the incident wave and the reflected wave superimpose to form a standing wave. And this portion where the amplitude is 0 are called nodes. Okay, and this area where the amplitude is maximum is known as antinodes. And this is the expression, this is the condition for the appearance of node. Nodes are observed at x equal to n lambda by 2. Antinodes are observed at x equal to n plus half lambda by 2. So you must study the derivation. Standing modes in a structured string and modes of vibration of string. So if you consider a string which is stretched between two fixed boundaries, and if we pluck the string in the middle, waves are produced. Standing waves are produced in that string. And it is not necessary that always a same number of waves or standing waves are produced on that string. The number of standing waves produced in each case may be different. So see, here we can see the first harmonic. And if the string vibrates in the first harmonic, then only one segment of the standing wave can be observed. And if it is a second harmonic, two segments, that means one complete standing wave is observed on the string. And if the string vibrates in a third harmonic, you can see 1.5 segments of standing waves on the string. So you must learn to draw the harmonics of a stretched string. Similarly, we discussed the harmonics in a closed tube and open tube. And in open tube, this is the first harmonic, third harmonic, fifth harmonic. From this it is very clear. In the closed tube, this is the case of closed tube. So from this it is very clear, all harmonics are not generated in the closed tube. Only 1, 3, 5. That is, odd number of harmonics are generated in a closed tube. But at the same time, in an open tube, all harmonics are generated. In an open tube, all harmonics are generated. That is the major difference between closed tube and open tube. Most of the musical instruments are related with this open tube. Okay. Next we discussed about beats. So what do you mean by beats? If you consider two waves of nearly same frequency but with the same amplitude superimpose each other, beats are observed. That means the resulting wave pattern will look like this. The resulting wave pattern will look like this. A regular rising or falling of resultant sound waves can be observed. This rising is called waxing of sound, and this falling of sound is known as waning of sound. Okay. This regular rise and fall of the sound is known as beats. And you must study the derivation for the beat frequency. Beat frequency is nu1 minus nu2, and the time period is 1 by nu1 minus nu2. Okay children, so with this we have completed our revision, and study well for your exams. All the best for your exams. So always follow a systematic study pattern, go through the major concepts, and apart from this, thermal properties of matters are the, and I haven't discussed anything from that chapter, but that chapter is also very important, and since it is very simple and no more derivations are there in that chapter, so that's why I just didn't discuss that, and you can easily go through that chapter and study the major concepts of that chapter. Okay then children, stay home, stay safe, keep learning. Thank you.